In our last video, we talked about log properties in a traditional sense and what's usually taught in pre-calc classes. Today I wanted to show you how log properties, and specifically the tool of a log table, was useful both historically and still today to be able to answer some questions. Throughout the video, we'll be using these particular log properties, and specifically this product property, this quotient property, and the power property. We won't use the change of base property today, although it's useful. The big thing that I want to introduce you guys today to is a log table. In the back of just about every textbook, every pre-calc textbook, Algebra 2 textbook, you'll probably be able to still find log tables, although they aren't used very much anymore since everybody has a calculator on their cell phone and on their in their back pocket and all that sort of stuff. But a log table was the tool used for making calculations all the time back before calculators existed. And I just want to show you briefly how this works. If I wanted to calculate a log of 3.4, nowadays I could just type it into my calculator, but we could look that up before by finding our log table, finding row 3, and going out until I see 0.4, and so this combination, 3.4, that's what log of 3.4 is, 0.5315. And you could find any logarithm with this table, even logarithms that you don't think are in this table. For instance, log of, let's go with log of 80, okay, I wrote 7, so we're going with 74. So, log of 74, you don't think 74 is in this table, but you quickly learned to write this as log of 7.4 times 10 to the first power. Put it in scientific notation. And then, by using the product property, we could split this up as log of 7.4 plus log of 10 to the first. And log of 7.4 is something I can look up in the table. 7.4 is this number right here, 0.8692. And log of 10 to the first is, well, since it's log base 10 of 10 to the first power, that's just a 1. And so log of 74 is 0.8692 plus 1. And I'm sure you could write that as 1.8692, but actually it's, for our purposes today, going to be easier to keep things separated like this instead of writing it as a single number. Now, you can also undo a logarithm this way. For instance, you could ask log of what number is, I don't know, let's call it 0.853. And to answer this question, you would have to look through the contents of the table and look for 0.853 somewhere. And 0.853 is somewhere between 7.1 and 7.2. So let me circle these numbers. And so 8.5 or 0.853 being somewhere between there means that if I'm looking up the number that gives me that as a logarithm, I could call that what, 7. Well, it's more than 7.1 and it's less than 7.2, and so I might say 7.15. And there were techniques that you could do to calculate what this number is more precisely than my just kind of guessing. I think that's called interpolation. If you're interested in that, I'm sure you could look it up somewhere. But we won't get into that much detail. But I do want to show you how these log tables allowed calculations to be done that couldn't be done otherwise. So, as I mentioned, these tables, log and anti-log tables, helped people, helped mankind to be able to do multiplications and divisions and exponents way before there were calculators, like hundreds of years before there were calculators. You could do this. So, I'm going to do one example, which is actually so simple, you're probably going to think, why even bother? But again, you got to remember, there wasn't any other way. This was the tool that was used. So I want to divide 89,000 by 27, and I provided a couple of relevant numbers from the log tables here. We can look them up as well if we wanted to, but just to speed things up, I looked up numbers ahead of time. So the process that we can use using nowadays notation is let's call 89,000 divided by 27. Let's call that x. And rather than getting out a calculator, which doesn't exist, or typing this, using long division on this, I'm going to suggest let's take the logarithm of both sides. So log of x is equal to log of 89,000 over 27. And by taking advantage of our subtraction quotient property, we can write this as log of 89,000 minus log of 27. And unfortunately, we don't have a log table that's big enough to go up to 89,000 or 27, but if we write those in scientific notation, then we can use our log table. And so that's 8.9 times 10 to the fourth, which would mean add log of 10 to the fourth. And then we need to subtract log of 2.7. And since 2.7 or 27 is 2.7 times 10 to the first, I'll have to subtract log of 10 to the first. And these are numbers that we could look up in our table. In fact, I've already done that for us. So 8.9 is 0.949 if you look it up in the log table. And 2.7 is 0.431. And I can do this division problem by effectively just doing a subtraction. Subtraction's way easier than long dividing. So 9 minus 1, 8, 4 minus 3 is a 1, 9 minus 4 is a 5. And so the log of x, which I admit is not what we want yet, but the log of x is equal to 0.518, and then I also got to deal with the bigness of this number, the powers. So this was 10 to the fourth, so log of 10 to the fourth is 4, and log of 10 to the first is 1, and if I subtract those, 4 minus 1 is 3. And so the bigness of this number is that it's something times 10 to the third. The something part comes from reverse looking up, anti-logging. And so if you look in reverse in that table, somewhere in that table, 0.518 shows up. That's what log of 3.3 is. And so to end this problem, we use the anti-log, the looking up idea, or in a modern calculator, we would do 10 to the 3.518 power, and that will give us our answer. But we're going to do this in pieces. The 10 to the 0.518 power, or the anti-log of 0.518, that's 3.3. And the 10 to the third power is the bigness of our number, the magnitude of the number. And so x, our answer, our desire, is 3.3 times 10 to the third power, or roughly 3,300. And if you actually get out a calculator and divide 89,000 by 27, the correct answer is, what do we got here? 3296.29 and some change and so on. But that's rounded to the nearest hundred, 3,300. That's exactly what we came up with here. But we didn't have a calculator. So, again, this might feel like overkill. Why bother writing this out? But maybe it was the only tool you had. And I'm not going to go through this example, but let me just show you a nightmare of a problem that really you kind of need to use logarithms for if there's no calculators. Let's do a gravity calculation. That was certainly done in Newton's time back in the 1700s and so on. Newton's law of gravity between planets is g, which is a number times the mass of a planet times the mass of another planet divided by the distance between them squared. Just a couple of numbers here. This is the force of gravity between things. So what are some of these numbers? G is the number 6.67 times 10 to the negative 11th. And the mass of Earth would be, I don't know, somewhere around 6 times 10 to the 24th. And the mass of the Sun, maybe, is something times 10 to the 27th, maybe. Let's call it 3 times 10 to the 27th. I don't remember exactly what these numbers are. And then we'd have to divide that by the radius, that is the orbital radius of the Earth around the Sun, so it's a pretty big number as well, something times 10 to the 8th or 9th, I think it is. Again, I'm making up these numbers, but imagine trying to divide that with no calculator. Even if you did want to use long division, this is going to be a nightmare of a problem. You got to do all these multiplications first, and then also do a division. A log process is, or the process we just did with logarithms, isn't really that much harder or bigger. You got a couple more things to add or subtract together, but you can break this up into maybe 5 or 6 logarithms that are being added together, and adding and subtracting, that's way easier than doing a multiplication. And so that's the real power of logarithms that's kind of lost in today's society with all of our calculators, in my opinion. Now, I want to end with a problem that's actually too big for your calculator to handle, and show you that how using a logarithm can extend the capability of your calculator a little bit. And so here's an example that I'm going to update a second. This is 2015, so let's call it 3 to the 2015th power, and see what does this calculate out to. So I'm getting out my TI-83 here and raising it to the 3 to the 2015th power, and it doesn't work. It gives me an overflow error. And so if that was the only thing I had available to us, we'd be out of luck. But we can do that same trick. We can take the logarithm of both sides. And so logarithm of 3 to the 2015th power. And this will allow us to still get an answer in scientific notation for this number. So we'll take advantage of the exponent property and pull 2015 out as a multiplier of log of 3. And this is something we can type into our calculator. 2015 is just a number, and log of 3 is a really tiny number, so 2015 times log base 10 of 3. The calculator gives me about 961. And here, the decimal numbers are crucial. I'm not going to round to 962, but I'm going to write some of these decimals out. 0.3993283 is what my calculator gives me. And this is what the log of my answer is. And I'm going to now undo the logarithm, which will be on the calculator, raising both sides on top of a 10. If we just do 10 to the 961.39928, that's still a gigantic number. And so we're going to do a little trick here. We're going to raise both sides on top of a 10. The 10 raised to the log x gives me x. And on the other side, we're going to split this up into two different parts. We're going to do 10 to the 961, and we're going to do 10 to the 0.3993283. The 10 to the 961 is the reason the calculator had a problem. You can't raise something that big. The calculator doesn't have that much space in its memory for numbers like that. But the 10 times 3, the 10 raised to the 0.3993283 part, that your calculator can do. And that is not a big number. 10 raised to the 0.3993283 is 2.508 and some more change after that. And this is what 3 to the 2015th is in scientific notation. It's a huge number. It's got 962 digits in it, the first couple digits of which are 2 and 5 and 0 and 8. So this, again, allows us to use logarithms to calculate things that we wouldn't be able to do just by typing them in. So we'll end with one more problem, 400 factorial. What is 400 factorial? Again, it's too big to type into your calculator. It will give you an overflow error. And so let's take the log of both sides. Log of x is equal to log of 400 factorial. And that means log of 400 times 399 times 398 and so on until we get down to times 3 times 2 times 1. So that's a really big multiplication problem. And it's going to take us forever to type into our calculator, and it will give us an error because 400 times 399 times 398 times 397 and so on is too big of a number for the calculator to handle. Here's where the log helps us. A log of a product, remember, is a sum of a bunch of smaller logs. And each of these things, log of 400, log of 399, and so on, all the way down to log of 2 and log of 1. Those are all relatively tiny numbers. Log of 400 is a number between 2 and 3, because 10 to the second is 100 and 10 to the third is 1,000. So this is a 2-point-something number, this is a 2-point-something number, and so on. Log of 1 is 0, and so I can add all those numbers up, and that's not that big. Now, it takes forever to type log of 400 plus log of 399 plus log of 398 plus log of 397. But if you've been watching this video, then you got nothing else to do. You might as well type in log of 400 and log of 399 and so forth. And I'm going to pause it a second while I type that in. And after doing that, I got 868.8064142. And like we did last time, we can break this up into two smaller pieces. When we reverse log, when we anti-log, when we raise both sides on top of 10, that will give us x back again. X is equal to 10 to the 868th. That we'll have to leave undone as the magnitude of our answer. and then also 10 to the 0.806142, and that is 0.806412. That is 6.403 times 10 to the 868. There's what 400 factorial is in scientific notation. And again, we are able to, by taking advantage of logarithms, calculate some things that are, well, impossible to do without them. So, thanks for watching, and I hope you can try this on your own sometime.